This talk is structured around the notion that it's basically for compiler implementers. So most of the topics here are staged around the module level flags and their equivalent fast math flags and how functionality is moderated and changed by each context and environment. So we'll start off by talking about how those flags are mitigated and introduced and where they're controlled at. First is a diagram, and I'll show you. Initially, the flags are introduced by front ends. They can be introduced by a driver environment as well. Just similarly, whatever your environment is that introduces those, it's going to be into the instruction IR, then mapped and first utilized in instruction simplify and combines and a few other optimizations that happen. Then on to DAG lowering, where they can be mapped into SD node if you're selection DAG, and then at instruction selection time into machine inster. And if you're global ISO, they go directly from instructions to machine inster. And it's worth noting that all three of these components that are managed either via get node or the builder environments are CSC safe now for flags as well as for instruction IR. So there's a number of models that we'll talk about and elucidate whether controls are mapped into and how they vary things. Those are the unsafe model itself, which is a module-wide scope and overrides the fast math flags, otherwise known as FMF. The fast math environment itself, which uses IR scope and for which all FMF is set, doesn't use the module flag at all. It just utilizes IR to map controls for each thing. And precise math, which is also IR scope and doesn't use FMF, but its main existence is for compliancy to IEEE 754. Now, we'll talk about how each of those flags map into those models and what their attributes are. The first one, the no sign zero flag, is in concern of whether or not we pay attention to the sign on arguments or results. Generally, it's mapped into arithmetic instructions and can be used in combination with some other flags. With unsafe, it's overridden. In fast math, the flag itself is utilized to map optimizations, and precise doesn't use it at all because it doesn't comply with IEEE. No NaN is an assertion that says that the value of NaN is not taking into consideration whether we're going to preserve the value or not. So in cases where we're in precise math, we would admit special code generation, and in the other models we wouldn't to preserve NaNs. And so we want to decide whether or not the flag is going to control that. And so unsafe overrides the no NaN flag, and fast math utilizes it. And again, another assertion flag is the no infinities flag. Once again, on operations, the input operations or results, we just changed optimization based on whether or not we're going to consider that value. And so one place where we utilize this is the floating point power optimization expansion. Or you might use it in some of your back-end implementations. So unsafe, once again, overrides it. It'll override all of these flags when you see them all. Fast math then utilizes the flags at each granularity of control, and it then is imposed as a conditional constraint for entrance through each of the optimizations, like in INS combining and simplify and DAG combining, etc. Fast math, just basically the main constraint there is to get the behavior and preciseness that you want. And so these flags are not generally utilized there unless you have a hardware constraint that requires it. ARCP allows reciprocal operations to take place, like a divide by approximate multiplication. It can also be used in context within square root and some other places, depending upon whether your hardware has some other applications for it or not. And once again, it's overridden by unsafe, and fast math utilizes the flag. Now contract, its main existence is really to mitigate the control of fuse, multiply, add. And it mostly is once again, unsafe overrides that flag and utilizes the module flag to control that optimization or set of optimizations that fold out FMA. Fast math uses a flag. And in precise, we ignored it. So reassociation is used. It's kind of interesting to mention these in combinatorics here, because recent changes in how FMAs are now controlled in their creation now utilizes these two together. There's a new rule you'll see in a lot of the DAG combines called is contraction that utilizes both of these flags in combinatoric. They're used to define whether or not a fuse multiply either propagates into others and can be associated into additional FMAs, or whether or not we're going to allow some reassociation or to facilitate contraction. Reassociation is also used with NSC to apply a various set of arithmetic folds and optimizations. And once again, it's like the others where the unsafe flag overrides its control, and fast math utilizes it. AFN, this is your approximation functions that generally get minted on hardware that are replacing things like sine and log and cosine. So your hardware you might want to implement some special functions that do maybe 2 or 3 times less latency on computing these values for the various input that they're considered, but they're not necessarily precise in nature, so they may not provide you with either behavior that is IEEE compliant or with precision that is IEEE compliant. Now, we'll talk about how precision and behavior are modified by these flags, and this is really about the notion of whether or not the order of operations is muted or whether IEEE behavior itself, meaning things like NaNs and Infinities, are propagated in the place where the user emitted them at the time or increment of time where they were supposed to be managed. And whether or not the precision has been altered by those, either the existence of flags or the optimizations that are controlled by them. Now, NSC is one that is changed by all three, or instigates the mutability of all three of these. In other words, we change operation order. We can, because of that a consequence, IEEE behavior and precision are also modified. NaN similarly does all three as well, but no Infinity doesn't. No Infinity doesn't consider necessarily, unless you have a hardware implementation that does something specific. Generally, the optimizations that are applied to this don't consider the order because they're mapping an expansion. So they only modify behavior and precision. ARCP, I guess, is orthogonal. The order of operations that's taken as input isn't changed. It's just a different representation. And so it's something that mutes behavior and precision only. Contract does all three, like the first two, and so does reassociation. And it's interesting to mention also that reassociation changes the order in which NaNs and Infinities occur, and their creation and because of reassociation, their non-existence. And so these values may or may not exist because of reassociations happened. It's worth taking that into consideration when you're considering behavior, and you may want to, say you're debugging a problem, you want to figure out what happened to your NaN or Infinity values. Maybe reassociation caused something to change the order in which they did or didn't appear. AFN doesn't do any order because it's basically it's the same function explained on either on hardware or some approximation of those functions used together. Generally, the way people usually implement these. They do modify IEEE behavior and precision though, and fast is really a roll-up of the worst of these. And so, any one of these constraints is lit, then all of them are lit for fast. Now we'll consider the attributes that are basically we'll define the attributes in the models for each of these math models and how they mutate things. So we think about what granularity of control each of these models offers, whether or not the IR flags are going to be changed or used by them, and whether or not NaNs and infinities are preserved, and whether or not we get best in performance or code size that we wanted from that math model that we're going to utilize, and if it's IEEE compliant or not. So unsafe doesn't use fine granularity control, it's module level, and everything that is underneath it is controlled by that. So IR flags aren't utilized, they're ignored. NaNs and infinities aren't preserved, but you get best in class performance of code and size, and you lose IEEE compliance through that. Fast math, similarly, has some of the shared attributes, but is fine granularity control because it doesn't utilize the unsafe module flag. But it does pay attention to flags, and so optimizations are then controlled at a fine granularity. NaNs and infinities are preserved based on the optimizations that are applied, or not preserved, pardon me, and we get best in performance once again of the code and in size. IEEE compliance is also not met here. And when you take these two into consideration for code generation, without the module flag, the lengths that we've gone to in the last couple years or so have brought these two models very close together in code quality and size. And so now you can, without the module flag, except for a few areas, there's still some minor changes in behavior when the module flag isn't used between fast and unsafe. But they're very close. And precise is also fine granularity control. And whether or not the IR flags are in the model is based on your implementation, generally not. They might be if your hardware has some constraints where it's required. And so we say, yes, they'll definitely obey the IR flags if you put them in. NaNs and infinities are preserved because the whole notion of the model is to be IEEE compliant. And because of that, we're not going to get the best performance or size. An interesting constraint to see is what happens to other models in the presence of unsafe. So here's an example. If precise exists, you lose your fine granularity of control that you had without the module flag. And you lose any controls that you had on the IR for subcontexts. NaNs infinities are no longer preserved, and your best-in-class performance in code is gone, mostly because the precise code that you asked for, say you got it from a library and you compiled that code into your unsafe environment, you may have asked for that precise code, which is in many cases considerably larger. And so there you lose your size and performance constraint. And because of that, you also lose your IEEE compliancy as well because of unsafe. Now, we've already touched a little bit on how unsafe changes behavior. We can drill into a little bit of the attributes. One is that any model, not just precise, but any model that doesn't utilize unsafe itself can be muted or modified by the unsafe module flag. So if you have a model that's other than this, maybe not fast, maybe you've got something else, some other subcontext model that looks like fast, if it's utilized within the auspices of unsafe, most of your guarantees that you've wanted to provide to your users is gone or will be gone. And the reason for that is, in part, because of the models that exist under it, like precise in this case, where we have a set of libraries that were compiled, provided in precise format. They're now optimized with the unsafe behavior. And so you've got huge codes that you've shrunk just a teeny little bit because it's underneath unsafe and because you emitted a large pattern that weren't as small as they could have been if you'd emitted them underneath unsafe. And now you no longer get the behavior that you wanted from precise, and you no longer get the speed that you wanted from unsafe, as if you admitted them. So you kind of have the worst of both worlds in this case. And then one of the main drivers of all this is the fact that reassociation is globally and locally applied to remove some of those constraints. And it's done through combines and through the reassociation pass itself and through various things that are done with reassociation, various phases. Now, an interesting new mode, mixed mode, is an application that may not be fast at all, where we could interleave IR with a mixture of flags, at some granularity of control. And so you could do this at the library boundary, you can do this in a function boundary, or you can do it all the way down to expressions. Basically, you can apply whatever control that you want in your emitted code by applying the model that knows how to manage the interface at these levels. And of course, you're not going to be using unsafe in that environment. And with that, you get the ability to use the other models that currently exist, like fast and precise, along with your new model. And you get defined behavior within each box. You also get fine granularity of optimization and no loss of generality. And you get a bunch of new contexts to manage your optimizations in. And what does it look like? It looks a bit like this. So mixed mode, however you want to define it, will pay attention to fine granularity of control within the box that has been defined in. The IR annotations are read wherever they're applied. NaNs and Infinities are preserved within their context, and best-in-class performance and code size is managed also as well and within context, and also IEEE compliancy. So you get whatever you designed into your box, you get in this mixed mode model. So, and then the boundaries really define where the interface is, and the generality can be lost at the boundaries depending upon what happens to code inside and outside the environments. So if you have fast connected with precise, you might generalize some of your results that precise created in your fast code. It's currently available in LLVM 8 that just went out a little bit ago. So the infrastructure is available. You have to implement to it to utilize it. We've done something like this at home at Apple because we're looking into models where we want to use a mixed mode approach. Now, we'll look at some comparisons in behavior and preciseness with how some of these models interfere with each other, or maybe just describe how the attributes are applied to each. The first is a FAD combine, and we're just going to fold two FADs together. In this particular case, we're going to use a initial value that's very large, and we're going to seed it with two constants that we're going to fold underneath unsafe or IR flags. And what effectively happens is that these two large hex values that you see wind up obliterating at each other, creating a 0. And you wind up with an FAD that's adding 0 to X and essentially providing X propagated to all the places where that final T3 was mapping to. So you get rid of quite a bit of code, but you get different behavior. And the opposite side of this is that we take into consideration what happens under precise is taking these operations in order, we produce a different value. In this case, the first add produces an infinity, which propagates to the second add. So it depends on what you want to do with your code. If you're more concerned about speed, you don't really care too much about whether or not behavior is maintained for IEEE, you do the top example and get the performance. But if you want something that keeps your precise values, then you want the submodel underneath it for doing precise. Considerably also, the fmul does, in this case, something that's an analog. Instead of behavior, this is precise context. So one of each I've taken in this. This is a very small number, and what we're going to wind up with is these constants that are folded out will produce a correctly rounded 0 that AP float produces for you. And because of that, the final result of the last multiply then gets propagated as 0 into all the places where it initially was mapped. And so you wind up with a lot less code, but with a different value. And the precision difference is that in the precise version of code, you get an actual number. And that multiply that's down at the bottom of that is then correctly rounded for those two numbers. It's also non-zero. So you get a different precision value based on what your input and your constraints were for your optimization or lack thereof. Now, fdivide also shows you a constraint underneath fast and unsafe that's different. In other words, we emit different code for different reasons. One case we want to get performance, the other case we want to get a precise result. Now, the difference between these two is really, in the half precision differences, is single OLP, but reciprocal operations can often reach a 1.5 OLP divergence between a precise result and a unsafe result in this case. So you want to remember what your range of variance is going to be if you're depending upon a particular result output. And so having the ability to control the models at a sublevel gives you a different container boundary about when you can expect to have your results modified or not modified. Now, our conclusions are with that we really want to try to get you to endorse this new model of doing mixed mode compilation. And by doing so, you can emit flags on the IR and then not utilize unsafe at all and get this fine granularity of control for these new boxes of compilation. And you can implement it today with the current infrastructure that's available. Mixed mode gives you a lot of abilities to do things that were not previously available with unsafe. Unsafe was just kind of a very large mallet to control optimizations in a single combinatoric. Now, future ideas gives you kind of an idea where we're going with some of these. And you can get kind of into the Wild West as far as FMF and unsafe goes for muting optimization control. In this case, we've got some other ideas as well, and I'll elucidate on those later. You can do function specialization for each of the FMF contexts for all your call points, or you can do the converse. You can inline them underneath a similar constraint, and pragma controls give you a similar constraint as well. So you can do these ideas of specializations in either context. And per function control replacement is really a kind of a permute replacement control methodology as well, where you can replace library controls and maybe have a set of canned versions that are FMF mapped and replace those with it. So you can have a lot of new flavors of things to do. And you can create some new math models, or we can add, like currently we're considering adding a flush to zero flag to FMF and maybe do some new combinatorics to things. There's initially setting up for this conference, we put together a blog, which we framed around it a thread in the LLVM dev called LLVM Numerics issues. And if you're interested in reading along with the various ideas that people are having, or maybe you've got some ideas of your own that you'd like to inject into the forum, please do so. Send mail into that forum. Or you could come to the BOF today at 4. And we can all discuss this and some other ideas that people have come up with that are elucidated in that thread. That is my presentation.
Thanks very much, Michael. I'd like to open it up for questions now. Please use the mics, or I'll bring one to you if you need.
Hey, do you have any grasp on so if you're going to add more FMA flags in future, and you've already got like a bunch of them, do you have any grasp on the extra complexity that's going to add to all of the optimization passes to like respect these, especially with adding more in future?
Yeah, there's been some studies done on that, and I think you want to send email to Sanjay Patel. He's done some studies on it. He knows who else has done it. Each time we do this, there's some combinatoric studies done on it to say what kind of complexity we're going to add to things. In general, it hasn't worked out to be a big overhead, though.
Okay.
Yeah.
That's good to know. Thanks.
Yeah.
Hi, this is Hideki from Intel. Thank you very much for this talk. From our perspective, we are actually interested in the constrained math so that we can preserve the exception behaviors and the precision together. That's one thing. And from the vectorizer perspective, we are interested in vector math and then how to preserve the value consistency, bitwise reproducibility between vector and scalar.
Right.
And within the vector, different microarchitectures and things, and different vectorization wheels. And from the OpenMP perspective, the OpenMP parallel for reduction, for example, actually overrides the reassociation of the underlying language. And we need to somehow define the default on which way we should be in favor of, whether we take the OpenMP directive and then override, or we actually honor the reassociation from the language to go. So yeah. So I'm gonna show up in the both to discuss
good.
some more.
Yeah, there's been some talk along those lines and along mass behavior for vectorization as well that kind of fits this motif.
Hi, Michael. Good job. I guess my question was about vectorization. And do the flags affect vectorization at all, or is the behavior expected to be the same?
It'll be a lot closer to the unsafe model because a lot of constraints are removed. I guess it kind of the question is really posed on which vectorization, because I guess you could make submodels.
Come to the BOF.
Yeah.
All right.
Yeah.
I was a bit confused by what you meant by mixed mode, and it doesn't really match with my current understanding of the state of things. So by mixed mode, do you mean you have the function level attributes coexisting with the fast math flags?
Yeah, you can effectively, it's for as many not unsafe models as you have, you could compile them all together in an application. And mixed mode is really the synthesis of how they all work together.
Okay, so it's not its own distinct thing.
Yeah.
Okay, thank you all very much. We'll have the next talk in about 7 minutes. Oh, one more question.
One more.
What about the library? What option will you use for all library you provide, if you provide a compiler? So you use the mixed mode or some provides mode?
Can you elucidate a bit more?
For one compiler, we needed to provide some library.
Oh, right.
Yeah, library. So which mode will you use because we needed to provide binary, not a source code.
It kind of creates an interesting problem with respect to libraries, because you could easily say yourself getting into, as a compiler implementer, delivering multiple library collections before the context. So if you have 3 math modes, you might want three collections of libraries to be consistent with them. Or you can just manage them within the context of the ones that you want to mitigate. So you could produce a precise library and a fast library, but that doesn't either one of them exist underneath unsafe auspices.
Oh, okay, thank you.
Yeah.
So to expand on what Michael said slightly, if you're only going to have one, it should be the precise one. But a number of the transforms here would license you to generate calls to reduce precision or an alternative implementation in some scenarios. So you could key off the fast math flags at the call site in order to make that decision. All right. Thank you, Michael.
Mm-hmm.